So let's start now discussing about processes and threads. So if you think about the reasons why you would like to have processes being executed as multiple threads, a very simple example we can start with is that of the Word editor. So when you use a complicated piece of software like, I don't know, Microsoft Word in this example, you do different things. You are typing characters, and while you type these characters, they appear on the screen. But you know that there is more stuff happening on the back. So the spell checker might be continuously checking whether what you type is correct or not. You might be printing a document in parallel and so on. Now the question here would be, if one process if only one process can be running at each CPU core at one specific point in time, because we have context switches. Why do we have multiple cores? And also, how is it possible that while the spell checker is running, I can still type characters instead of just being blocked because the process is doing something else? For instance, checking what I type, or printing a document, or checking if there are updates to download and so on. So this is solved because we have multiple threads that are executing the same process. Now, don't think about threads like something that is different from a process. In fact, what I said during the last lecture about processes is not, let's say, external to this discussion or orthogonal to this discussion. What we discussed so far, it's basically executions in which there is a mapping between one process and one thread, okay? A thread is just the sequence of instructions that belong to a program and that you are running one after the other. So if you assume that one process has only one thread, it means that when you execute this process, you can only run one instruction at a time, and which one you run depends, of course, on the text section and how the code is organized. When you have a multi-threaded execution, it means that you can run multiple lines of code that belong to the same process at the same time, in parallel at different cores. Notice that it also means that you can context switch between one thread and another thread when these two threads belong to the same process. So you can run instructions that are about the spell checker of Word, but then do a context switch and run instructions that are about, I don't know, the feature of Word that checks for updates, or the one that is reading your characters and printing them to the screen. Okay. Simply put, you have multiple program counters, and each one is referring to the next instruction that will be run for the same process. Okay. Now, this I mentioned the very first time. You have trade-offs in space and time complexity, and when you improve one, you usually pay higher price in the other. If each process is single-threaded, then the entire information that you keep for the process and about the process at the operating system level, it's unique. If you have multiple threads that can run the same process, then some information that is specific to the thread needs to be duplicated, as I am showing here, with, for example, dedicated registers or dedicated stacks for the variables of the function you are running, or the next function that should be run, and so on. Now, in practice, most modern applications are multi-threaded, and multiple threads run within each application. Here you have some examples again about Microsoft Word, but you can make examples with many other programs. The reason why we use multiple threads is because it takes less time, it's lighter to create a new thread that belongs to a certain process than it is to create a process. Because when you create a new process, you have to create all the information about the process. Since threads share information. They don't need dedicated information about the entire process. When you create a thread, it takes less time, so it's more efficient, okay? And this can simplify code and increase efficiency. And the common example you have here is that of a multi-threaded server architecture. So if you write a server that is listening for requests, so basically it's waiting for someone to connect and then ask for something, you can implement this with multiple threads. You can have a thread that is listening, and whenever someone connects to ask something to the server, then you can spawn a new thread and tell to that thread to execute the portions of code that are related to how you check for the answer, how you produce the answer, and have the listening thread going back to listening again for the next request. This allows for responsiveness because the listening thread is always listening. It takes very little time to start a new thread to answer while going back to the next question, okay? And if you look at the benefits of multi-threaded applications, you have responsiveness, resource sharing, economy, and scalability. And they are described in this slide. You don't need a multi-core architecture to justify the existence of threads. Even if you have a computer with a single core, you might still want to have threads, so that while a certain part of the process is waiting because it has to do something with the disk, you can run another part of the process that might interact with the user, for example. The second thing is that if you want to use a multi-core architecture, you don't necessarily need threads. You can have single-threaded processes. And I'm not talking here about the fact that you can run different processes like Word on one core and Spotify on another core. You can actually write programs like the example I made last time for Google Chrome, in which you span several processes, and then you have these processes communicate with inter-process communication. Since they are different processes, they can use different cores. So it's not that if you want to take advantage of a multi-core architecture, you need to have threads or multi-threaded processes.